Okay, so here's another example of a problem that can be done using the second fundamental theorem of calculus, sorry, the first fundamental theorem of calculus in our book. I'm forever going to mix those up because of the way our book does it. So this is, sorry, so this is find the derivative of the function x to negative 3, integral from x to negative 3 of fourth root of t squared plus 5 dt. So this is a derivative of integral situation, but the thing you have to recognize is that the second fundamental, first fundamental theorem of calculus is very, very finicky about how it works. In other words, the theorem states that the derivative of the integral from a to x of f of t dt is equal to f of x. Okay, fine, but we need it to match exactly. A has to be a constant and the variable x has to be on top. If it's not, then we're going to need to somehow manipulate this in order to make it so. So fortunately, we have a rule, this property of integrals, that says that we can switch the limits of integration simply by negating. So this is going to equal the derivative of the negative integral from negative 3 to x of the fourth root of t squared plus 5 dt. So now I can simply now I can use the properties of derivatives to bring this minus sign outside. It was the derivative of a constant multiple like negative 1 if something is equal to that constant multiple of the derivative. So I can bring this negative sign outside. That's going to be negative d over dx integral from negative 3 to x of the fourth root of t squared plus 5 dt. And now I finally have exactly the type of expression, or it should include this here, that the first fundamental theorem of calculus can help us evaluate. So that's going to be negative, and we know that this expression with the red bracket underneath it is just going to be the fourth root of x squared plus 5. So that's the answer. So the trick here is that I had to manipulate the integral in order to get it into this form. It has to be constant going up to x, or it just does not, or the fundamental theorem of calculus does not work. Okay, so we have a slight variation on the problems of the first fundamental theorem of calculus problems that we've been doing. We have evaluate the derivative of the function defined by integral from 3 to x squared of sine t squared dt. So you might look at this and say, oh, okay, well, I've got the exact form. I've got the constant in the bottom. I've got x, not quite in the top, but let's just ignore the fact that it's a squared. And of course, that's sort of the way I've been doing this for a while, so I know that that's how people think of it. The squared is just the x squared is just too pesky of a departure from what the theorem is looking for. Unfortunately, we do have to deal with it in some way. The theorem is very, very specific. It requires that we be finding the derivative of a function that looks exactly like this. It has to have an a in the bottom and an x in the top. It can't have anything else. So here's how we would do this. Let's say this is another way the theorem was stated. It said we can define f of x to be equal to the integral from 3 to x of sine t squared dt. In that case, it's certainly the case that f of x squared is equal to the integral from 3 to x squared of sine t squared dt, right? In other words, if f of x is defined in exactly the way that we want it to be, with the form that the theorem is looking for, I can convert it into the problem we have simply by replacing x with x squared in this function. So what I'm really trying to do is this bracketed expression here is now capital F of x squared. What I'm really trying to do is find the derivative of f of x squared. So what that means is that f of x squared prime, I'll even write it in the form that they're looking for, the derivative d over dx of f of x squared is going to equal, that's going to equal f prime, but this is by the chain rule, it's going to equal f prime of x squared times 2x. That's how the chain rule works. If I take the derivative of this composite function, then by the chain rule I do derivative of the outer, apply to the inner, then times the derivative of the inner. So what we know is that, let's see, so what is f prime of x? F prime of x is just going to be the derivative of this function. And we know how to take the derivative of that function because of the first fundamental theorem of calculus. So f prime of x is going to equal sine of x squared. In other words, I'm just replacing the t squared with x squared. So so let's see. So that means that what I need is f prime of x squared times 2x. So that means f prime of x squared times 2x is going to be equal to sine of x squared squared, because I'm replacing, where I see this x, I'm replacing it with x squared. So I have to square it twice, and then there's a 2x on the end. So this is equal to sine x to the fourth times 2x. That's the answer. Okay. Is there an easier way to think about this? I mean, what I'm doing here is sort of the theory. Let's see if there's just an easier way that we can solve it. So let me just write this out again. Derivative 3 to x squared sine t squared dt. So what we're going to do basically is we're going to do the same replacement that we would have done under the fundamental theorem of calculus. We're going to write this as sine x squared squared, because every place I see t, I'm just going to replace it with x squared. And then I'm going to take the derivative of this thing. So does that lead me to the same place? Yeah. So it does. So basically what we're doing is you're just going to do this when you see an expression like this where you don't have an x but you have some function of x in the upper position. You're just going to do the exact same thing. You're going to replace the t with whatever this expression is on top, and then you're going to multiply the whole result by the derivative of that. So what you're really doing, if that feels like what you're doing is the chain rule, the answer is that's exactly what you're doing. You're just doing the chain rule. You're just finding the derivative the normal way and then multiplying by the derivative of the inside. Let's just do one more of these where there's a little bit more of a complication. So let's find dy over dx where y equals x times the integral from x squared to 3 of sine t to the fifth dt. So the thing about this is also involves a product rule in order to do this, and it really lays bare the fact that the first fundamental theorem of calculus actually is just another rule for finding a derivative in just a very, very, very strange situation. So we can say that, let's just write this as y prime. So let's say y prime is going to equal x times the derivative, sorry, I just want to write this in purple. Y prime is going to equal x times the derivative of this thing. Well, we know how to find the derivative of that, because the derivative of that is going to be, let's actually work that out here. The derivative of the integral from x squared to 3 of sine t to the fifth dt is going to equal negative derivative integral from 3 to x squared of sine t to the fifth dt, which is going to equal negative sine of x squared to the fifth. In other words, I just replace the t with the x squared, but now I multiply by the derivative of the x squared, so that's 2x. Okay, so we now see what the derivative of this expression is. So going back to our product rule, we have x times the derivative of that expression, and that's going to equal negative 2x sine x to the 10th, once I simplify that. And now I need to do plus, the derivative of x is just 1, and then I have the original function. So this is x squared to 3 sine t to the fifth dt. And that's the answer. So the thing to recognize is I just sort of did a product rule where that was f and that was g. So I did f times the derivative of g plus the derivative of f, which was 1, times g. And by the way, it shouldn't bother you that there's a t in this problem, because the fact is the function is still defined in terms of x. T is what's referred to here as a dummy variable because it only exists within this integral. Remember, if we were actually going to evaluate this integral, which we're not going to do, what we'd be doing is we'd be finding an antiderivative of sine t to the fifth and then plugging 3 and x squared in. So the t would disappear. It's okay to leave it here because we're sort of implying that we will replace it in the future. So that's how you would do that problem.